Hello, so today we are talking about normal curves and the standard normal distribution. This goes in section 2.1 of the Practice of Statistics textbook. Feel free to go there and look on for more examples and extra practice. So before we dive into new material, we need to talk about some notation updates. So up until this point, we have focused on sample notation. And for sample notation, the mean we said was x bar, or that x with a line above it. This was my mean. And the standard deviation was sx or just s. So this is my sample notation, and this is what we've been dealing with because we've been looking at samples of data. I've given you a data set, and from that set, or that sample, we found the mean and the standard deviation. But we also have what's called population notation. And the more we move into this year, the more we're going to see population notation show. For populations, the mean is this kind of U with a tail. We call this mu, like mu. It's a Greek symbol. So mu is a U with a tail. And standard deviation, we call this sigma. And it's kind of an O with a line above it, or like a really loopy-loop R. So you may see population notation show in sample problems, and we're really going to see it with the normal curve. So normal distributions are a type of density curve. So density curve is a new term for this course, and it is the area under a curve adds to 1. Or an area has to add to 100%. So that's kind of a definition of density curve, and that's the component of a density curve that we really care about, that the area adds to 1. So normal curves have a mean of mu and a standard deviation of sigma. This is what a normal curve looks like. It's unimodal and symmetric. And the standard deviation we can estimate by looking for the change in curvature. So where my curve starts to go down and then loop back up, or kind of go down and then become concave up, that's where my standard deviation is. This is more calculus related, so we talk about it and we mention it, but don't stress out if you're like, I don't know where that is. So normal curves will take on different steepnesses. You can see all these curves are unimodal and symmetric, but the smaller the standard deviation, the more concentrated the data, which means the steeper the curve. Remember, my standard deviation is my spread. So if I have a small spread, then I'm going to have more concentrated data, which means my curve is going to be like this blue curve and be pretty steep. But if I have a very large standard deviation, or my data is more spread, it has a wider range, I'm going to be more like this gray curve that just kind of goes up a little bit and then comes back down. So the smaller the standard deviation, the steeper the curve, and the more concentrated your data is. So key point number 1, normal curves are a special type of density curve. Remember, density curves add to 1. We write this super fancy notation. Make sure you get this key point down. Well, we write down every key point, but make sure that you get that notation. We write that notation to state a distribution is normal, which is why I have the n, with a mean of mu, so the mean comes first, and then the standard deviation of sigma, which comes second. You will see this notation. Sometimes this will be all a problem gives you. And this is plenty of information to do all the work we need to do. So how do I know if something is normal? How can I say this is a normal curve? Well, there's two methods. Method one is to look at what's called a normal probability plot. These will be given to you. You will not have to create these plots. But what this plot is it plots your data against the z-score. So if I look at this graph over here, I can see my raw scores are my vertical axis, and my standard normal values, or my z-scores, are my horizontal axis. Most z-scores we've seen go from about -4 to +4, or -3 to +3. So a normal probability plot, if the data is normal, it should create a straight line. But we see this one kind of makes a little S shape. It doesn't make a straight line, which means this data set is not normal. It does not make a straight line. It makes a little curve. And normal distributions should make a straight line. And that's what we look for when we are given a normal probability plot. So outliers are points far away from the line. So like this would be an outlier. This would be an outlier. They're far from kind of where most of the data is. Check the axis. The z-score can be on the x or the y. So I could always flip this graph so that the raw scores are the x and the z-scores are the y. So check your axes to know what you're looking for. So here are some examples of skewed right and skewed left data. So skewed right data means I'm concentrated on the left side, and then my data goes out and is more spread on the right. And we can see that here. I'm really concentrated right here, but the further I get on my y-axis, the more spread my data gets, meaning I'm spread to the right. The points on the right are more spread. Skewed left, my points on the left are more spread or more skewed. So this curve would look something like this. Very concentrated in one point, but then very spread out on the left side. The second method is where we're really going to put our attention though. Method 2 is called the 68, 95, 99.7 rule. So take a minute to write this down and then I will explain it. Okay, now that you've written it down, if a distribution is normal, then it must follow the 68, 95, 99.7 rule. Well, what is that rule? That rule says that approximately 68% of the data is within one standard deviation from the mean. Then 95% of the data is within two standard deviations of the mean. And then 99.7% of the data, but usually we see this as 100%, is within three standard deviations of the mean. So we're going to take a look at what that means graphically and what that visually looks like. But just remember, these are approximations. We may get like 65, 94, 100, or 67, 92, 99. It's not always going to be exactly those numbers, but we want to be close. So this is what it looks like on a graph. If I think about my mean in the middle, if I add one standard deviation, well, I'm going to be a little bit above the mean. And if I subtract one standard deviation, I'm a little bit below the mean. And this rule says that 68% of the data is going to be within that range. And then if I do the same thing with adding two standard deviations, so I go out another standard deviation on both sides, now 95% of my data is in that range. This rule ensures that I'm going to get a unimodal and symmetric curve. So key point number 2, We determine if data is normal by using the 68, 95, 99.7 rule, or by making, and really this should say looking at, normal probability plots, because they'll be given to you. So we're going to take a look at an example that puts all of this into practice. So it's a really tangible example. It says here's a dot plot showing the weights of 36 Oreo cookies. So I have 36 dots because I had 36 cookies in my sample. The mean is 11.392. So this is a sample of 36. So I would say X bar is 11.392. And the standard deviation, or SX, is 0.081. So how I put the 68, 95, 99.7 rule into practice is by doing something like this. If I add one standard deviation to the mean, that gives me this range right here of 11.311 to 11.473. So I took the mean, I added one standard deviation, and subtracted one standard deviation, and that gave me a range of 11.311 to 11.473. Well, now if I look back at my table, 11.311 to 11.473 would be that range right there, and if I count my dots, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So 26 out of my 36 dots would give me 0.72 or 72%. So 72% of my data is within one standard deviation of my mean. Well, then I can do the same thing for two standard deviations. So two standard deviations is over here in the purple. It would give me this range because I subtracted two standard deviations and added two standard deviations. So my range is 11.23 to 11.554. So when I come back to my graph, 11.23 would be like right here to 11.554 would be right around there. Well, I just added 1, 2, 3, 4, 5, 6, 7, 8. I added 8 dots to my 26 that I already had, so 34 out of 36 gives me 0.944 or 94%. So 94% of my data is within two standard deviations, and if I go out 3 standard deviations, you see my range goes from 11.149 to 11.635. And if I look at my data, that encompasses everything. So 36 out of 36 gives me 1, which is 100%. So this is looking at the 68, 95, 99.7 rule. 72% of my data, which is really close to 68%, is within one standard deviation, 94% is within 2, and 100% is within 3. Since those are close to 68, 95, 99.7, we can say that Oreo cookies are approximately normal. So why does it even matter if something is normal? When is this going to be useful and practical in our class? So if we think back to what we've been doing, we've been talking about the standardized variable, or the z-score. So notice this z-score has that new notation of mu and sigma. because with the normal curve, we use mu and sigma for the mean and standard deviation. So we can combine z-scores with the normal distribution with this unimodal symmetric curve to find the area under the curve, and the area under the curve equals the probability of getting that value. So what we're going to be working with is this thing called the standard normal distribution, which is a unimodal symmetric normal curve, but it's centered at the mean, or when my z-score is 0. So now my x-axis is going to be my z-scores. And we can use our z-scores to find the area under the curve, and that's going to tell me the probability. So we're going to be working with this in class in very tangible, real ways. To determine if data is normal. So I will see you next time. Have a good one.